Yeah, thank you. So I'm going to be talking about a project called the Northwest Mineral Province Data-Driven Mineral Exploration and Geological Mapping. So obviously that's my title slide, but really the title slide should look like this. So this is work that was done by CSIRO Minerals and Data 61. And I really acknowledge the authors there. So Dave Cole, Lachlan and Bashek were the main contributors across this, as well as a whole host of other people in those two teams. So this is a work that the CSIRO Data 61 and CSIRO Minerals undertook, and we were the recipients to that data and those models. But I just acknowledge that all this work was done by them. Any problems with the interpretation or conclusions that come out of it is all on me. But their work is there. The report is live, and in Rick's series of webinars we put up online, there are talks from both Dave Cole and Bashek about this work as well. So if you are interested, please get in contact with them, get in contact with us, but also watch those talks because they are great talks. So I guess we've seen this slide yesterday from Helen, talking about the discovery drought going on in the Northwest. And I have a slightly different interpretation of this data, because as you see, as we start to discover a lot of these deeper deposits, sort of in the 80s and 90s, that's when we had a step change in our geophysical understanding. We had our regional airborne surveys that started to give us that penetration of depth and that understanding of those systems undercover. So I see this as seen as a step change. And I think the next step changes in our geoscience look will be airborne gradiometry, put my geophysics hat, but also machine learning and application machine learning in geology to take that next step change to help the discovery. So I guess where this work came in is as part of our start of our geoscience data modernization program, which Kate and David are going to talk about. We're really looking at showing the value that we hold in our open file data and really showcasing what could be done with that data if we make it all open, if we make it all discoverable, and if we make it available with machine learning techniques. So this is a sort of an early pilot to showcase the outcomes that can come from having a clean data set that is easy to machines to read and bring into whether you're using Python or whatever code to run these machine learning programs. So the work was undertaken, as I said, by CSIRO Minerals and Data 61, really to investigate the strengths and abilities of different machine learning techniques. There were several techniques they used purely on open file data. It was also to improve our own understanding of how these machine learning techniques may be applied in the future and showcasing the open file data availability in that Northwest Mineral Province and what can be done with a whole suite of great quality and quite voluminous open file data. And the work here was really focused on the Northwest Mineral Province. I have a link down here for the report, but obviously with the QR code on the programs here, you can find all the data sets done under the SREP. So I'm going to talk about a couple of the techniques and a couple of the examples they did as part of this. So firstly, I'm going to talk about something we did a long time ago. So Courtney and myself did a program called Combi in 2013, and that was doing a Common Earth model and then using a weights evidence approach to understand the mineralization so I'm just going to move. No, I can't move that. Oh well. No, it's gone. Understanding the statistical evaluation of the spatial relationships between evidential criteria we use for exploration and the mineral occurrence in that area. So that was the end result of that work, where we used 14 mineralization sites in that Combi block to train up the model against a whole bunch of evidential criteria and then stack them up to create a mineral potential model. And that's basically showing where those criteria, multiple positive correlated criteria, are overlapping. So the first thing we did with the Data 61 team is we tried to do that same project using the same inputs and the same data set to build a logistical regression model of the same data sets. So this is the Combi model with a different view. And you can see that the training sets down here. So Ernest Henry is sitting down here and E1 out to the side there. And then we have the same model using a logistical regression machine learning technique. So here you can see it captures a lot more of the structural complexity and understands the relationship with the granites a lot better. But the real problem we had with using logistical regression here is it wants a whole lot more training data than we currently can provide to it. So really the question was, is mine sites the best training data set for a mineral potential model? Or is prospectivity modeling really the best use of machine learning in geoscience? And I think the answer to that one is no. But we have some other examples of some work we did with them. So the next sort of sub project we did in this was a geological classification. So this is using a random forest classifier, purely using surface and geophysical covariates. So remote sensing data, gravity, radiometrics, and magnetics. And it was really run across the entire outcropping area of the project area in the eastern succession. So this originally trained the data on the surface geology. So this is the simplified surface geology over here. And then we took 1% of each of those surface geological layers and trained the model on the geophysics to then predict what the entire area would look like. So that's the model's prediction using 1% of the input, the surface geology input. Then over here we have the probability. So really that's how confident the model is. So the yellow here, the model is very confident, it's fitted it well. And when you get into the blues, the model is less confident. And then you can see the difference. So where it's orange, it's the same lithology, and where it's blue, it's a different lithology. So I think I've got that expanded in our next slide. Yep, so there's our using 1% originally of each class or each lithology to train the data. So but that's probably a quite high amount of data set to be using as your training set. So here we used 415 random sites collected randomly. So you can see over in the right image here, these are the random sites that we used as our original training set. And here's the output geological model, which is still quite a reasonable geological model for that area. It's still very confident down here that it's got the model working well, but you can see the difference now. There's a lot more blue. So that's really showing areas that we can come back and maybe review our current geological mapping of that area. So this is not how we're going to map everything in the future, just using machine learning, but it shows the areas where we may want to reevaluate our mapping or go back and have those targeted mapping programs to see why the model doesn't agree with our current geological modeling based on our geophysical data sets. So here's an example of a local classification of the same model. Here we use 10% of the data to train it and then ran it on the other 90%. And you can see it has a pretty good understanding out here where it's got some good contrast, and it sort of starts to fall away a bit over to the side here. But that was a quite well-populated model, well-populated geological area. As we move into more sparse geological understanding, the model really starts to struggle to build that classification, and it starts to put a whole bunch of this red unit out into the east, where there is no control, basically. So the next step here, and I guess a lot of this model was testing out the limitations of some of these techniques. So we use that same input data set, and we use 2 points per lithology, and we try to train the model over the entire area, whether it's outcropping or undercover. And you start to see at 2 points per lithology, doesn't do a great geological model based on our solid geological interpretation over on the right here. At 20 points, a little bit better. At 200 points, it's a little bit better. But really, this is some limitations about what your training data is using and what you're trying to build the model against. So if the training data is, in this case, we're training on apples and we're trying to predict oranges in that space. So the next step, and this is I think one of my favorite examples done here, because I can bring in my geophysics background. Basically, what we did here was geology, or it was granite, not granite, was our classification here. So my geophysical rock collection of granite, maybe granite, and probably not granite comes in great here. So this is using the outcropping area again, and we use 600 points across the surface to train up. There were 6 classes basically. So we had our 5 granitic suites in this area. So the Williams Narraku, the Wonga batholith, the Calcadine Leichhardt, and not granite was the final area. So we were able to train the model using those 6,000 points. So this is our outcropping surface geology in our granite, not granite scheme. And this is the random forest model prediction for that. And again, it's quite confident in a lot of the areas that they're not granites, and it's correct, they're not granites. But it starts to struggle in some of these areas. But this is a great tool again, and we can understand why this happens with the next slide. Because obviously, not granite is a major part of our training data set. Because it's voluminous nature in the area, the Williams supersuite is well represented because there's a lot of training data in that. But as you come into some of the smaller granitic suites and you only have a couple of of samples that have been trained on that, it's less accurate at predicting that, which makes a lot of sense. So if we zoom down into a particular area here, we can see in this part of the southern part of the model, here's our surface geological map, and here's the model prediction. So the surface geology has this little embayment, which is the granite, and the model doesn't have that, but it's quite confident that it's got it right. Now, this is obviously a problem with using the geophysics to train on surface geology, because you might have 10 meters or 20 meters of a geological unit on top of that granite, but really in terms of what the geophysics sees, it sees the whole way through the model and it says, that looks like a granite to me. So this is really being aware of what you're training it against. This is a great example where you may come back and go, oh, we're not sure about why the model's so confident there. We could go back and have a targeted mapping program in that area to understand why the model is very confident and why the model wants to put that there. Again, pushing it to the limits and seeing how much silly questions we can ask of it. We use the same training data set to predict the entire area, whether it's outcropping or not outcropping. So it was trained again using the geophysical and the DEM response of the outcropping granites, and it really doesn't work in the covered terrains. Obviously, this is a great example of that garbage in, garbage out technique we talk about in machine learning. We're asking the machine a question, the machine will give you an answer, but if your question is poorly formed or the premise is poorly formed, it'll give you an answer that doesn't make any sense. So this is why pressing the magical big red do machine learning button and coming back with a response and moving on with your life is not a great idea. The real advantage of a lot of this machine learning is to understand why the model isn't working, or understand why the question is working, and then come back and maybe rephrase your question or ask a better question entirely. The third example and the last example I'm going to talk about is what they call anomaly detection in interpreted geology. So this is using an unsupervised technique called one class SVM, or support vector machine. So basically what it did is we trained in the SVM, trained over the whole outcropping model, using the geophysical data, gravity and magnetics basically for everything, and it defines a domain for each geology, each class in that, and says this is the optimal mean geology, geophysical response for those means. We call that a hyperplane, and then we can see as part of the model, how the model works here is you seed it with an amount of anomalous, or how anomalous you think your geology is. So here we're saying we think 50% of our model may be anomalous, and then it will say these are the areas that are furthest away from that perfect mean for each of those lithological classes. Now this is probably completely disingenuous to the geological mapping work done in this area. It's far too anomalous in the area, so we can bring it down to 10% anomalies, and you can start to see some of these, the purple areas are anomalous. You can start to see some clusters appear. So some of these clustering areas where that particular area is assessed as being anomalous, maybe where you've got an unknown mafic intrusion or a granitic intrusion in that area, maybe the map boundary is in the wrong place, but the model's starting to say that it doesn't agree that this area over here is the same as this Mulunga Basin. That's the Mulunga Basin. Mulunga Basin geology that we trained it against. So there may be something in that area, or maybe it's shallower or deeper than we expect in that area. And if we come down to 5%, you can see now what we want. A lot of the anomalies are now finding their way on the edge of those bodies, which is what we'd expect, because you start to see where the geology is mapped as a two-dimensional surface. We're really using three-dimensional geophysical understanding to understand the entire block in that area. So when you get to the edges, you might start to see some areas that aren't as consistent with the geophysics as the center of that unit. But we do start to see some areas, and that's maybe where we come back and look at reevaluating the map in those areas. So again, I've gone quite fastly through a bunch of those, and there were some other examples in that report, and I would encourage you to read that report. And now I'm going to go completely on my own and talk about some limitations in regional machine learning. So most data sets we have regionally are really sparsely distributed with a non-uniform distribution. So you can see this is from some work that David's done that he'll present on as well. The non-uniformity of this data set is really hard to train on. You can see there's obviously a mine or some exploration activity going on here. And then as you step out, there's less and less and less drill holes, and there's none out here. And so we have some problems around the limited amount of continuous data sets in the area, where we get to basically the only one that's continuous is geophysical data. And then because of that, you come into a dimensionality problem. So machine learning likes to work in multiple dimensions of data, But as we move further and further out of known areas and into greenfields areas, we really have two dimensions. We have the gravity and the magnetics for all of those. And another side of that dimensionality, again, is what I mentioned before, is where we've got a two-dimensional geology we're trying to interpret, but we're using data that's seen the entire crust in the gravity or a fair amount through the crust in the magnetic. So you're using a three-dimensional data set to train a two-dimensional geology. So again, we have a strong sampling bias as well in our data. So where you have mineral activity or exploration activity, there's a really high sampling bias, be it in geochemistry here. And then where you have less activity, which is where we want people to be exploring, we have basically no data. So an example here, just north of us, that's our faults and veins in an area just north of Mount Isa that's been obviously very well explored. So if we were doing a training model, we could train it against the distance to faults or the distance to how many faults are in an area, and we'd probably get a really good fit so we could start training the model on. But as you step a bit further north at the same scale, this is when you get into that outcrop subcrop area. The fault probably still exists. We just don't know it because we haven't mapped that area extensively. And as you go undercover, there's no prospectivity here because there are no faults, which is an obviously fallacious claim. There are a lot of faults up here, I imagine. We just don't know about them. And we only know about the big ones rather than down near Mount Isa. We know every single fault that has an offset of, 14 centimeters. And I guess the other thing, one of the other limitations here is what we can measure versus what we do measure. So we obviously use geophysics a lot to understand alteration, but there are a lot of things that geophysics shows, be it different geological types, mismatches in the mapping, alteration, graphites that may be there. So we use these things as proxies because it's the best we can do. And also the question is, are we measuring the right thing? So I found this on LinkedIn and I really enjoyed it. So here are my training data. I'm looking for a male, was born in 1948, raised in the UK, has been married twice, lives in a castle, he's wealthy and famous. So I'm starting to cut down on what I've got, but I can match that to Prince Charles or Ozzy Osbourne, who both satisfy all those requirements. So even though I've measured a lot of things, I still have two disparate data sets that fit that same result set. And we do that a lot in geology, where we measure a lot of things, but are they things we should be measuring? And are they things that give us information about the mineral deposits we're looking for, or are they just giving us various information we don't need to care about? And then I guess the last one is the prospectivity modeling is really driven. It needs a lot of training data sets, and training against a mineral occurrence or training against a mine really gives you a limited training data set. So with all those limitations in mind, I think machine learning has a place in GSQ, and this, I've got my view here because this is not GSQ endorsed. This is what I think machine learning will place in our moving forwards in regional geology. So I think some examples of augmenting our existing geological mapping processes, using that geological classifying to understand the areas we need to reevaluate our current mapping, or focus our new geoscience work on areas which may disagree with that anomaly detection. We might find areas we need to understand where new data would enable better prediction, so where we can reduce the uncertainty or increase the confidence in the model by getting new data in an area. And I think we'll get to the stage, hopefully, and David and Kate will be talking about this later, where we can iteratively update models as new data becomes available. So rather than building a model and saying, this is our model, and I can put up Combi that we did 10 years ago, we can have models that build themselves as we keep going and keep getting new data in there. And I think the key point that Kate and Dave will talk about after tea, as well as using machine learning with the GSQ, we have a big job of enabling and supporting those who want to use our data sets for machine learning into the future. So my last slide here, obviously the Northwest Queensland data and geological mapping report showcase some regional applications of machine learning, but machine learning should be an iterative process of exploration discovery within the data. I've got my big red do machine learning button here, but that's not what we should be doing. The iterative process is in asking those questions, getting a result from the machine learning, seeing why that result has come, understanding the context of that, and then build another model to better understand the data. Really helps you understand the data, and the end result you get with the big drill here targets isn't really what you're going for here. It's that understanding of the relationships within the model. Machine learning is not a panacea that's going to fix the entire industry, but it's another tool that we can add into our tool belt to help understand our geological and geophysical and geoscience data. So that's it for me. Thank you.
Any questions for Matt? Internet.
Helen can ask them.
We've got a few online, so I will read them out for Matt. So the first one is, I think, back to the previous talk, actually, for Dom or Matt. Probably Matt. When will the AEM inversion be released?
Very shortly. I'm just working on a way to release it in a manner that people can bring into a GIS or bring into a potentially Euclidean model or geoscience analyst space that means I don't have to deal with double array channels in a database, which is horrid. So really looking at creating a data set that can be used on any tool like Dom was able to put up some of those lines in geoscience analyst. But yeah, we're working towards getting that up.
Excellent. Good to hear. Dom, going back to your talk and your talk that you shared with Joe, what's the time frame on the updated interpretation of basement depth?
There's not a set time frame. That was a forward-looking statement.
I will assign you sometime next year. And then this one is on your talk just now, Matt. So great work from Josh. Is a threshold being used for the SVM predictions?
I don't think so. I think it was just that anomaly, that new value that you give it, you seed it to understand that. But it was basically the hyperplane defined by the entire geological map.
What does the data structure look like in the SVM predictions when you taper the anomaly thresholds?
I have not looked at that, but I'll talk to Bashek and Dave about that, because that sounds, we could look at that.
In other words, does the predicted anomaly, or do the predicted anomaly frequencies mimic real geochemical frequency distributions and abide by some natural fractal distributions we see in nature, like Benford's law inverse square?
I don't think they'd worry about geochemical anomalies so much, but definitely the geophysics. What I think it maps out is some of those areas may have a bimodal population. So you think about the Corella, which is nearly that grab bag of geology that we don't know what to do with. So there's mafics in there, there's felsics in there, there's calc silicates, there's sandstone. So there'll be a lot of anomaly across the Corella formation itself. But in our model, we've called it the Corella formation. So it's trying to fit a hyperplane to really a multimodal population of geophysical responses.